All right, can you hear me? Yeah. It's my great pleasure to open today's distinguished lecture of the Institute of Microengineering. And we have the pleasure and honor to welcome Professor David Horsley from UC Davis. So Professor Horsley is currently professor in mechanical and aerospace engineering at UC Davis, and who received his PhD previously in mechanical engineering from UC Berkeley in 1998. So he's also a co-director of the Berkeley Sensor and Actuator Center at UC Berkeley, and of course, since there he is involved in all the developments of microsystem technology, MEMS, and the like. And of course, in his career, he was also chair and co-chair of many of the renowned conferences that we know, IEEE MEMS, Transducers, Sensors, and this, among others, led also to awards such as the NSF, the National Science Foundation Career Award, and the Outstanding Junior Faculty Award at UC Davis. So his research has also led to many applications. So not only has he co-authored more than 150 publications, but 20 patents have resulted from his research. And we will see today maybe a little bit how this technology transfer into real-life applications has worked. And as part of his research on MEMS transducers, ultrasonic transducers, he then co-founded the company Chirp Microsystems, which was just acquired by TDK, and we will be very happy to learn about not only the technology, of course, but how this adventure successfully was transformed into the company. So please welcome David Horsley.
Thank you, Niels, and thanks everybody for attending my lecture this morning. So as Niels said, what I'm going to talk about today is piezoelectric, micromachined, ultrasonic transducers, or PMUTs, for consumer devices. And I'll just give a little bit of introduction to myself. So I had a little bit of an unusual background when I came to UC Davis because I spent 5 years working in industry before I came back to academia. So I worked at HP Labs for a little while, what used to be HP Labs before the company was split into Agilent and HP. And so I worked alongside Rich Ruby, who some of you may know about the F-bar. It's probably the most successful piezoelectric MEMS device today. It's made of aluminum nitride used for cell phone filters, and in your cell phone you probably have something like 20 of these, the filters there. And so Rich at that time was working with aluminum nitride and trying to get good piezoelectric materials there. And I remember at the time, they asked him, how did you have the right frequency? They did some experiments where they actually inserted one into a cell phone and used it as a duplexer. And they asked, well, how did you have the right frequency for the phone that you're using? And he said, oh, easy. We had all frequencies on the wafer. Just pick the right location and you get the right frequency. So anyway, there is a connection to that. That was like in the late 90s. And so I thought that aluminum nitride was a material that had potential for lots of other uses. And so that's one of the things that I'll talk about today. I am a co-director of BSAC. And so BSAC is in the US, we're only partly funded by government money, and a lot of it is from industry funds. So companies like Texas Instruments and Qualcomm and ST Microelectronics and others have funded my work, and we've collaborated with them in a lot of this work. So I guess part of the story here is I had an unusual background because I came from industry, and then a lot of the work that I do at the university is actually sponsored by industry, and that is very unusual in the United States. So typically in the US, people are funded pretty much exclusively by the government, and so it's quite unusual to do things that are kind of the edge of academic research and almost like kind of practical industry R&D. And there are certainly some challenges to that we often end up being kind of at the edge of things that people think of as being kind of proprietary and patentable, and so that has its kind of unique challenges and advantages, but it is a little bit different from what other people do. And certainly if you have other questions about that, I'd be happy to answer them. So I'm going to talk about ultrasound today. Some of these slides at the very beginning I actually took from a Chirp presentation. So Chirp is a company that I co-founded based on the work that we did at the university. And we had to explain to kind of the normal person that you run into on the street, they actually don't know what ultrasound is. In fact, we were very careful to use the word ultrasonics in what we do, because when you say ultrasound in the United States, people think about medical imaging. And so the first question we always get is, oh, medical imaging, that's great. I want to see better pictures of babies. And we have to explain, well, that's not what we do. So we call it ultrasonics. And ultrasonics are actually in common use today, but people aren't aware of them. So if you have parking assist sensors on your car, those are ultrasonic transducers. And this is showing a picture actually from Audi of what, they kind of conceptually show you how these work on the car bumpers. So each of them has a non-overlapping field of view, and they're doing what's called a time of flight measurement, or a TOF measurement, where they emit a pulse of ultrasound, and they listen to the returning echoes. And the time of flight of those echoes, because you know the speed of sound, you multiply the time of flight by the speed of sound, and it gives you the distance to where the target is. So again, to explain this to kind of the layman, we call it sonar or echolocation. And the way it works in cars is that these sensors have non-overlapping fields of view, and they can tell you if there's an object to the left. And in this image, it's quite hard to see, but the zone here on the driver's display is showing sort of red here, because there's a pole that's over here on the kind of the right front of the car, and the ultrasound is detecting that. So part of the reason we show this is to show that it exists today. And so why is it used in automobile? Why not just use a camera? Because that today is everybody's response is, well, can't you do it with computer vision? And the answer is that it's really hard to tell range with computer vision. And so these ultrasound sensors are really kind of the best way of measuring range. And for automotive applications, it's important that they are immune to noise. It's another question that we get a lot is, oh, isn't it, when there's loud sounds, won't that interfere with the ultrasound? Well, clearly we all know that this works in cars. And actually on Teslas, they use the ultrasound for the lane detection on the freeway. And maybe now Tesla is not maybe the best example of the autopilot system, but nevertheless, they do use it. It does work. So even at freeway speeds of, let's say, 100 kilometers per hour, you can use ultrasound to see things to the side of you. And again, I use this to explain because today people are really very aware about computer vision and cameras, and they're also very aware in the United States. They think, well, self-driving cars or autopilot, aren't they all using radar, and aren't they using LiDAR, and isn't that the best thing to do? And the reason that they use ultrasound for the lane detection is that it's the best thing for short-range detection. So radar has kind of a dead zone where it's close to the car, and so if you're doing lane detection, especially in Europe, right, the cars in the other lane are quite close to you, and that's right in the blind zone of the radar. And so they use sonar because it's the best thing to do for close detection. And so for parking, you want to detect things that are close by. And if you wanted to do like pedestrian detection, that sort of thing, again, I'd argue that ultrasound is kind of the best way to do it. So ultrasound is very robust. We know that it works in these automotive applications that are very demanding. They're safety critical. And we don't care about the color of the pole next to us. So we should detect it whether it's black or white. And again, this is a problem for optical sensors, for what are called infrared time-of-flight sensors. When you have a black target that has very low reflectivity, and so it's hard to measure those things. And then also, a lot of these optical sensors don't work in bright sunlight. So basically the sun is a very bright, particularly like for infrared sensors, the sun is a very bright source of IR. And so they overload the receiver. So your detector will, doesn't matter how sensitive it is, once it's overloaded, you can't detect anything. And so that's one of the problems for particularly like applications where you want to work outdoors, why optical sensors don't work very well. So this is one from Bosch here, and it's next to a euro coin, and so you know exactly how big it is. They're pretty big. They're also used in drones here. This is in a DJI drone, so DJI is like kind of the biggest manufacturer of drones today. And you can see on the bottom of this drone, there's two downward-facing ultrasound transducers. And so these are used to do hover height stabilization. So it basically holds the drone level. And there are some other ways that people have been trying to do this using pressure sensors for altimetry. But again, in terms of measuring the height above a surface, it's really the best way is to do it with ultrasound. And you can see these are these little, they're a little bit smaller than this one, but they're still probably the size of like a US penny inside. So ultrasound is commonly used. It is sort of the best way to do range finding today. It's just that today it's pretty big. It's made with a relatively old technology, like a bulk piezo that's been bonded to a metal frame and then put onto a printed circuit board with a lot of discrete components. So conventional manufacturing, lots of discrete electronics. It's really too big to go in consumer applications. But it is really the best solution for range finding today. And there are other kinds of places you'll see these things. I was actually in a smart parking garage recently where they were doing occupancy sensing of the parking stalls using ultrasound sensors that were looking downwards. So it's a really good way of seeing the distance to things, and so you can detect whether there's a car in the stall or not. So at Chirp, what we sought to do was we thought that this was, like other sensors that MEMS has displaced, we could take all the kind of advantages of MEMS and apply it to this application, take the things that this is best at and just make them a lot smaller. So we have inside this, we take all these discretes and we put it into an ASIC. So it's like 100 times lower power than a conventional sensor. 1,000 times smaller, so 10 times smaller in every single dimension. And it gives you the same, we're still limited by the same ultrasonic physics, and so we can have the same kind of performance that you would have in a bulk transducer, just in a much, much smaller device. And so we have what, sometimes the acronym used by DARPA in the US is what's called C-swap. So that's cost, size, weight, and power are really the advantages over the existing technology. We kind of check all those boxes with MEMS ultrasonics. So this was the kind of the compelling argument that we had when we started this. I mentioned early on that actually when I started this work, it was really not motivated by the idea of making anything commercial, but I saw that we had an aluminum nitride deposition system at the university. It was actually at UC Berkeley. And I saw really all the success that had been done in RF MEMS, and I thought, well, we could use aluminum nitride for something else. So we were looking, really, we had a technology, and we were kind of in search of an application for it. So we didn't start from the application side. You'd like to think that we saw that there was a need, and we really wanted to address this need. No, we had a material, and we thought, what could we do with this? So we started from the bottom up, and we were kind of lucky that we found the right thing to do with it. So let me tell you a little bit about commercialization, and then I'll get into the technology part of it. And I kind of debated about where to put this, but I think that this is one of the things that is kind of unique about this work, and so I think it is quite an interesting story. So it was 10 years ago, actually, that we got the first funding to work on this, and so it was from DARPA, which is a Department of Defense research agency that funds probably most of the MEMS work in the United States today. Comes from DARPA. DARPA had a program they wanted to do. It was actually Amit Lal, if some of you know Amit Lal, who's a professor at Cornell at that time. In 2008, he was program manager at DARPA. And Amit is actually a guy who is a long-time ultrasonics guy. Actually, I remember the first MEMS talk I ever saw was Amit had made a zinc oxide microphone, and so that was another thing that was kind of inspirational to me at the beginning. So Amit had a crazy idea about doing soldier navigation using better inertial sensors, and so we got a program to make actually inertial sensors in aluminum nitride, and we had as an aspect of that was to make an ultrasonic transducer. So we were working with analog devices. Analog devices was working on the gyro component. We had an accelerometer, and then we had this ultrasound thing. And basically everything else didn't work out. The only thing that actually made it from that program was the ultrasound. And it really was not exactly what DARPA wanted to do. But we had a bigger program, and we were able to sort of sneak this little thing in there that ultimately became this successful technology. So DARPA programs are about 3 years long, and so after 2011, we ran out of money. The students weren't graduated yet, and we still didn't have something that was particularly compelling, and so we had to keep going. And luckily at the center, we had companies that were willing to kind of give us a little bit of money. By this time, we were down to 2 graduate students. So myself and my collaborator, Bernhard Boser, had to find a way to fund each of us 1 graduate student. So we needed to find $50,000 each to keep this going. And we did keep it going, and so those students were able to graduate. And so part of the reason I mention this is that one of the things that we did that is different is that or maybe what I would say is the kind of the hallmark of success is you have to be persistent. And so we could have said at the end of 2011, we could have declared success and moved on to the next DARPA program, but we were stubborn and we said, well, we're going to keep pushing on this and see if we can keep going. And sometimes in the face of people saying, you know, hasn't this all been done before, and CMOS are better, but CMOS haven't been successful, and so maybe there's no point to doing this. So we were persistent. We try to find, you know, 2 years worth of funding by any way possible to keep this going, because we thought that it was important and it was leading in an important direction. So one thing that I'll say to you is, if you're like starting your career, first of all, like I was unconventional. I kind of got a different start than a lot of people did. So try to be unconventional, do things that are a little bit different. And the other thing is be persistent, right? Even when people tell you that what you're doing is maybe wrong or maybe not the hottest thing to do today, you need to be persistent because it takes time to get these things to work. So don't be discouraged. So at the end of 2013, the students graduated and we started a company. And in fact, the students were more enthusiastic about it than I was. So in fact, one of the students, Richie Przybilla, actually was the guy who applied for this National Science Foundation grant. The National Science Foundation in the US will fund small companies. So we got what's called a Phase 1 award, which is $150,000 US. And so we started the company on the basis of that. Essentially, January of 2014 was really when operations started. We incorporated in late 2013, but really started work in January of 2014. So we had $150,000. We had 4 people, and you have to. Phase 1 is designed to be 6 months long, but you have a 6-month gap where you have no money because you're applying for Phase 2. So you really have to make a go of it for a whole year on $150,000, which with 4 people is really not possible unless you're willing to work for free. And so we basically did that. So fortunately what happened is we had a CEO who joined at the very beginning, and she was a very shrewd business person. And so towards the end of 2014, she was actually able to negotiate $1 million contract with a big consumer electronics company that I cannot name, but that really was what made the difference. So we kind of didn't work for anything for all of 2014 because we had to make stuff, right? So with $150,000, I mean, you guys may not know how much it costs to do your work, but it's expensive, and so people were not getting paid. And so it was like at the end of 2014, we got $1 million, and so we all got paid essentially for the whole year at the end of the year. So then from 2015 to 2014, so that was the very beginning. Those were kind of the lean period, and again, it was like about 4 people at the very beginning, scaling to 5, then 6 people. So then from 2015 to 2017, we raised $2.7 million from VCs and Silicon Valley angel investors. We transferred the MEMS production to a MEMS foundry that I cannot name. And we actually started at a small kind of prototyping laboratory and kind of proved the process on 8-inch wafers, which was kind of key from the very beginning because we knew we wanted to have high volume. So we started on 8-inch wafers. Then we later transferred to a big production foundry. We developed a production ASIC that was designed in-house and is today manufactured at TSMC. And we developed a packaging technology, and we transferred to a big, what's called an OSAT, an outsourced assembly and test facility in Asia. So all 3 pieces of it, the MEMS, the ASIC, and the packaging, we got all those things done. And so actually by the end of 2015, we had that finished. And I can show you some chips here. They're the ones that were in the picture. But basically that chip has not changed since the end of 2015. And the rest was really kind of about growing applications for it and kind of building customer contacts and that sort of thing along the way, and eventually kind of hiring more people to kind of join the company. So as Niels mentioned, then in the end of February of this year, we were acquired by TDK, and we formed the 4th MEMS business unit, or at least that's the intention. We were only sort of 1 month or so into the acquisition, and so a lot of this stuff hasn't happened yet. But TDK, they own InventSense, and so they have in their 4 MEMS business units, they have a motion unit, which is gyroscopes and accelerometers. That's sort of the core technology of what is InventSense. They have a microphone division that is made up of what used to be the analog devices microphone and the EPCOS microphone technologies that kind of got smooshed together. And then also more recently they started an ultrasonic fingerprint division, which I'll talk about later today because that is based on some technology that we licensed to them. So we developed the fingerprint sensor at the university, and this is a different model of university technology transfer. So one way is to take your stuff and start your own company, and the other way to do it is to take your stuff and make patents and then try to license those patents to companies and have them commercialize it. And so I guess I've had experience with both of those things. It's maybe a little bit too early to say, which is going to be more successful, because the fingerprint sensor hasn't quite yet started shipping. They're sampling it, but it hasn't started shipping yet. And so Chirp is kind of in the same state, actually. We're sampling parts and we'll begin shipping later this year. So we'll see whether the licensing method is the better way to go, or to start your own company. Certainly, if you are, I'll make I'll tell you honestly, I probably get $1,000 a year in licensing revenue, and so maybe if they go into production, I'll make a little bit more money from it. But licensing isn't, in my experience, it doesn't pay very well. So it's nice to see that you have practical impact. That's great, and I think that it's important, and we collaborate with companies, and so it's good that they get some reward out of the collaboration. But certainly, starting your own company is certainly, it pays a lot more. So that's I guess what I would advocate is that rather than trying to find somebody that will commercialize technology for you, you should do it yourself. So with that in mind, let me talk, kind of getting into the technical part of the talk. So I'm going to start with some history and motivation, and then I'll talk about ultrasonic transducers in the air, a little bit about time of flight range finding and phased array ultrasonics, and then I'll finish by talking about the ultrasonic fingerprint sensor, and we'll see how much time I have for everything. So I mentioned earlier you should be persistent, and I actually was at a DARPA meeting recently, and they had a slide that said, we have more than enough technologies. All we need to do, we don't need more. What we need to do is pick the ones that are going to be successful and invest more in those things. So what that slide was trying to say is that in many cases there isn't a lot of new stuff to be done. There's a lot of things that people experimented with, but they didn't really take it all the way to completion. And so there's a lot of work in the past that you'll find where people tried things. And so don't be discouraged by the fact that people tried things. But maybe there's a reason why it didn't succeed at that time, and maybe there's something new today that could make it successful. And certainly that was the case with us. So PMATs have been around for a long time, so more than 30 years. And I say more than 30 years because this is probably not the first PMAT paper. It was just the first one that I could find. And so this is from 1983, and this was a zinc oxide PMAT, and it even had there's a zinc oxide transistor on the die here as well. And these people worked at it, and presumably they had somebody who was like their zinc oxide person who probably ran the tool. But it was very hard to make the piezoelectric materials in those days, and so making one wafer, and if you had a device on it was good, was quite a challenge. So thanks to the people like Paul Meralt here and other groups that have really invested in piezoelectric materials technology, things are different now. So the fact that these people were not successful was partly because it was a little bit too early, I would say. CMOS have also been around for quite a long time, since 1994. This was the first surface micromachined PMAT from Stanford University. And so they have a lot of ideas in this paper where they talk about low-cost array fabrication and integration with electronics, and these are modern ideas. And so you might think that starting in 1994, that maybe 10 years later that people could do all of these things. But actually the surprising thing was it was only 2 years later that a group from Siemens, so some of you know Christopher Herold from ETH Zurich now, so he was at Siemens in those days. And so they actually made a fully integrated CMOS array in CMOS, and so each of these little hexagons here is a CMOS, and this is a 30 by 30 array, so it's actually quite similar to the fingerprint sensor that we made. It's just that, 1996, wow, it's a long time ago. And so one question is, why hasn't this technology really appeared commercially, right? Because you could make integrated CMOS, and so how come they're not in the medical diagnostic tools that we use today? Well, if you look at inertial sensors, a lot has happened in the last 2 decades. So in the 1990s, the gyroscope looked like this, and today it looks like this. So it's MEMS, basically the MEMS gyro did not exist in the 90s, and this year something like 3 billion gyros will ship, 3 billion MEMS gyros will ship, and so kind of a revolution has happened in inertial sensing. But not so much in ultrasound. So if you bought a rangefinder in the 1990s, it would look like this, with lots of discrete electronics here. You can see through-hole components in dip packages, and you can look closely. This is the ultrasound transmitter, it says, and over here is the receiver, so there's two of these things. But if you bought one today, it would kind of look the same, actually. So one thing that happened was integrated circuits have come a long way since the 1990s, and so now all of this is on an ASIC. This happens to be a Texas Instruments product. But here's that big old ultrasound transducer, which is basically the same. This is a sealed one, but otherwise it's the same as the one that you would have bought in the 90s. So the IC technology has changed a lot. The ultrasound transducer technology has not changed a lot. So one question is maybe why. So part of it, what I'm going to argue is that there's some things that changed over the last 20 years. And so there are things that we could do differently. So the first thing is the piezoelectric materials have greatly improved. As I mentioned before, so aluminum nitride is a pretty mature technology, PZT also. And there is a very well developed manufacturing infrastructure that's out there. So when we started Chirp, we didn't have to buy a tool, we didn't have to teach somebody how to handle a MEMS die. So you will find if you go out there, we toured around and there were many, there's probably 10 or so MEMS foundries that can do production today. A smaller number of them, maybe 3 or 4, that can really do high volume production, but nevertheless that stuff didn't exist in the 90s. If you were going to start to make MEMS, you had to be ST or Analog Devices, and you had to build a plant to do it, and now you don't have to do that. Also, equally important, like the packaging and test suppliers are very well aware. So we just went to people that knew how to package microphones, and there are lots of places in China and Taiwan and other places that know how to package microphones, they know how to handle the die, and so we didn't have to teach them any of that stuff. So there was basically no learning curve, there was no investment that was required. So you can do a lot of this stuff a lot more cheaply and a lot more quickly than you would have had to do even, let's say, 10 or 20 years ago. The other thing is that the market is quite different now. So there is a very strong pull for new sensors in various applications, from Internet of Things products, drones, autonomous vehicles, virtual reality. These are all places where sensors are very important. And so again, this was not really the case in the 1990s. If you think about it, in the 1990s, if you bought a computer, it was this sort of beige thing that sat on a table, and now we all carry them in our pockets. And so there's a lot of, these kind of revolution in computing technology has meant that sensors have become a lot more important. And then the last thing is that was important for the fingerprint sensor that I'll talk about later is that it was just decided that every phone would need a fingerprint sensor. Now that's not true of the iPhone 10, and so we'll sort of see how that continues, whether the Face ID technology takes over or if we'll see more fingerprint sensors. And there certainly are reasons why Face ID is more convenient in some situations and less convenient in other situations. And so we could have a discussion about which way is the better way to go. But for now, let's say there's something like 1 billion smartphones that are shipped today, and so roughly 1 billion fingerprint sensors are needed, and so that's a pretty big market. So let me talk about air-coupled ultrasonic transducers. There is this proof in nature that ultrasound is a pretty good way of seeing things. So bats and dolphins and whales use ultrasound. It's amazing what bats can do. They can target little tiny things like mosquitoes from 80 centimeters away. Now they have very large receivers here, so that's kind of an advantage to them, which we won't have with the MEMS device. If you look at existing ultrasonic transducers, they have the advantages you can generate a lot of pressure. They're not very efficient at coupling to the air because the acoustic impedance of the piezo materials is very high, and so you can generate a lot of vibration but not necessarily generate a lot of sound from that vibration. And so typically you need some kind of a matching layer. These are all too big for consumer electronics. This is the smallest conventional transducers. This is what's called the surface mount device that Murata makes, and it's 5 millimeters on the side. But these are all dumb. They don't have any ASICs in them. There's there's no smarts, and so they need a lot of discrete electronics, and typically they need high voltage, so something like 10 to 20 volts or even higher for the transmit signal. So with micromachined ultrasonic transducers, we have much lower power. So the ones that Chirp makes, and I have some here I can show you. This is a US penny, so these are about 3.5 millimeters on a side. They operate as low as 15 microwatts, and so in comparison to, say, optical sensors, it's orders of magnitude lower power. We have a couple of products that we made. One of them works to 1 meter, and one works to 5 meters. 5 meters is a really long distance to measure with a tiny little chip. It's kind of amazing that you can do it, and that's probably not the limit. We can probably go to 10 meters or more. And we do all the signal processing just like a modern MEMS inertial sensor. It doesn't just send the gyro signal out there. It's got some kind of a microprocessor on board. In our case, we have a 16-bit microcontroller inside the IC, and that takes up about 1 square millimeter of silicon. And so then the sensor is capable of operating autonomously because it's got its own processor on board, so there's no need for a host processor to be triggering the sensor. And I have a bunch of videos. I'll maybe just show a couple. So this is showing an example of, there's 4 of them in a tablet here, and this is like a very simple gesture interface. So there's kind of simple gestures like raising your hand. You can do more complicated things like these spiral gestures and things. And this is real, it's not fake. So this we developed for, I think we showed this, it was probably January of 2016. So we haven't really pushed very far on this kind of air gesture sensing, although it's sort of interesting because this is one of these things that sometimes ideas, they are popular for a little while, and then the interest sort of fades, and then they reappear again. And so this is one that has been kind of reappearing again, and there's some rumors that Apple is looking at some simple kind of air gestures for the next iPhone. So we'll see whether this becomes important. It's not an area that we've pushed too hard in, but it is something that maybe will make its way to products in the coming years. This is kind of a smaller version of the same thing in a smartwatch. This was a prototype, so the sensors are actually here. There are 3 of them in a watch band. And so what it's doing is it's tracking this person's fingertip motion next to the side of it. You can see the path. And then it has a little gesture classifier that's actually recognizing what the script was that was written there, and then basically displaying a clean number. So we actually did, in fact, embed this in a smartwatch. It's running on a little ARM processor, what's called a Cortex M4. And so in the smartwatch, what that's normally used for is for the activity detection. So in the watch, it has a gyro accelerometer. And for pedometry, it basically runs some kind of algorithm in that M4 that interprets those motion signals and then tells you what you were doing, whether you were running or bicycling or walking. So what we did was we overloaded our firmware onto that M4. And what you saw there with the classifier that was identifying the strokes and everything, that was all done on that M4. So you don't need a lot of processing power to do this sort of thing. And again, these are the same sensors. There are 1, 2, 3 of them here. And remember I mentioned that it was like the end of 2015 was when we really had kind of production versions of those parts, and then we were kind of developing these applications around the same sensor technology. So those are some applications. I have a few more that I could show you if we have time later. I probably won't have time. I think I'm getting a little bit long here already. You guys know about micromachining. So what we do is they're very much like microphones. We use a DRIE process to stop on a membrane. The membrane is made up of a multi-layer of piezoelectric materials, electrodes, and kind of a passive elastic layer. We can make arrays, and we did early on make arrays. This is an example of a 7-element array next to an ASIC that was designed to handle up to 10 transducers. And so we had a lot of results on phased arrays. What Chirp has made in production is actually a single transducer, so it's very similar to a MEMS microphone. It only has 1 diaphragm on the chip. because we thought that was kind of start with what's called the minimum viable product, do the simplest thing first, and then do other more complicated things later. I mentioned that CMOS have been around for a long time. CMOS, it turns out, are not very good at transmitting sound in air because basically in the kind of the analogy between circuits and acoustics is that it's the velocity multiplied by the acoustic impedance is what gives you pressure. And the acoustic impedance of air is very low. It's much lower than the acoustic impedance of water. And so that's basically what our body is made of. So when you're doing medical measurements, you don't need a lot of velocity to generate a lot of pressure because the impedance is so high. But in air, because the impedance is very low, you need a huge amount of velocity. And we are limited to low frequencies in air because you can't transmit at high frequencies. It's absorbed by the air. So you're limited to something like maybe 200 kilohertz is about the highest frequency that you can practically transmit over any substantial distance. And so when you're talking about low frequency, high velocity, that means large amplitude, large displacement. And so with CMOS, because you have this vacuum gap, to have, you need several microns of displacement to get any reasonable sound pressure level. And so you need a very large vacuum gap on the order of, let's say, 3 to 5 microns. And so with that kind of gap, you need very, very high voltage. So most of the CMOS will operate at something like 250 volts. So in comparison, a Pima is also a capacitor, but it's a solid dielectric, piezoelectric dielectric material. And so we don't have anything that impedes the motion. So we can move as far as we want. And we could make this layer as thick or as thin as we want, and it has nothing to do with the actuation. So we were able to get microns of displacement, and we do it typically at something like 10 volts. And we can generate that kind of voltage with a charge pump. And so that part that I showed you runs off of 1.8 volts, and we just generate the high voltage internally. So this is what the devices look like. I realize this is a MEMS talk, and I don't spend a lot of time talking about MEMS, but they're pretty simple. So this is an example of a university-type device. It's not exactly what the chirp devices look like. In the early days, we're using, for example, like 2 layers of aluminum nitride, roughly a micron thick, about 500 microns in diameter. This is showing one that has kind of a central top electrode. And when we apply voltage, we can actuate up and down. And in the early days, we were operating around 200 kilohertz with a bandwidth of about 10 kilohertz. And so these are photographs of what these devices look like, from hexagonal arrays to sort of square arrays. This is 37 elements. This is a 9-element array. And this is a close-up photo of a single device. And you can sort of see through the membrane layer. It's sort of semi-transparent at these thicknesses. And so then again, people also ask, why don't you make them with PZT? It turns out that as a receiver, this is actually from one of Paul's papers, in fact. I think this table is taken from there. So basically when you're transmitting, if you don't care about power, if you just want to know how much pressure you get for a given input voltage, then you only care about the piezo coefficient. And so there, PZT is the best material. So as a transmitter, PZT is the best material. But as a receiver, essentially you're going to divide by the capacitance of the device, and so you're going to end up dividing by this dielectric constant. And so because there's a factor of 100 difference here, that factor of 10 here is basically reversed as a receiver. So aluminum nitride is about 10 times better receiver. It turns out that the product of these two things is KT squared, roughly KT squared. It's roughly the piezoelectric, the electromechanical coupling coefficient. So still PZT is a slightly better material if you're talking about both transmitting and receiving. But there is one catch, and the catch is that we are usually limited when we transmit. We are limited by mechanical nonlinearities in the membrane. And so it's not that we can't, we could get to higher SPL by just cranking up the voltage with aluminum nitride, but at some point what happens is we have nonlinearities, and so we get basically a 2x increase in the voltage doesn't get you a 2x increase in the SPL. So that's sort of a bad trade-off from an efficiency point of view. So usually we operate at the limit, kind of the edge of the linear operating region. And that, for devices that we make today, happens around 10 volts. And so really the advantage of using PZT would just be that we could make the same device and get rid of the charge pump. So instead of operating at 10 volts to transmit, we could operate, let's say, at a volt or less. We wouldn't need a charge pump at all with PZT. But the charge pump is not really that hard to make. So, so it's not solving a huge problem. And on the receiver side, you're always going to be, that's kind of where you really want to put all of your effort. So the transmitter, as I said, we do about as good as we can, and there's really nothing that we could do short of, we should improve the MEMS design. But in terms of the MEMS design that we have today, there's not much that piezo materials can do for us for transmitting. But for receiving, actually, that's kind of where we're going to be limited by the performance of the materials and the amplifier that we have. And so you really want to design the best receiver possible. And so for that purpose, aluminum nitride is really the best material. So that's kind of where we ended up. And it was fortunate because, like I said, we didn't start from the beginning like really doing a deep optimization. We actually had a material. There's the joke that says, like, when you have a hammer, everything looks like a nail. So we had aluminum nitride, and so it looked like everything was, we should make everything with aluminum nitride. It turned out that we were right, but some of that was luck. So I know that I'm running a little bit short of time. I am going to kind of jump over some of the time of flight range finding stuff. Let's go to, I'm going to talk about phased arrays. So phased arrays, here we used like a two-dimensional array of transducers. This was a DARPA, you can see this was a UC Davis labeled on here, and somewhere BSAC should be on there as well. So this is a phased array. They're spaced at half a wavelength, and at 200 kilohertz, the half wavelength is about 0.9 millimeters. So this thing is something about almost about 7 millimeters in this direction. So you get an increase in the sound pressure level. It increases with the number of transducers. The power increases with n squared. And you can make a very narrow beam when you use a phased array. It's basically a property of increasing the aperture. So as you have a large aperture, then you get a narrower beam. And so this is just showing, this is measured data from a single transducer. So what we do is we take a Pima and we put it on a rotation stage, and we measure the sound pressure level with a microphone. And the radial distance here is the sound pressure level, and so you can see it's pretty uniform. This actually is probably, so more careful measurements would show that we do have some, there is some variation in the sound pressure level. It's very rare for us to get a perfectly hemispherical beam pattern like this, but they're almost omnidirectional. When you use these same things in a 2D array, then you can make a beam that is very narrow. And so this has a sort of a 3 dB beam width of about 10 degrees. And this is 7 elements across. It's the same transducers, just now we're using them, all of them on the same die. And so you can make something that's kind of like an ultrasonic laser beam. And you can, even by controlling the phase of these devices, you can sweep this thing over the full field of view that you have with the single transducer. And so just showing that the sound pressure level scales with the number of transducers. And so actually one of the tricks is for doing the, that idea that I talked about sweeping the beam, that's what's called transmit beamforming. And we basically never did that in the air because it's too complicated and it's slow. So if you wanted to take a fast image, you've got to sweep the beam. And if you're going 5 meters out, that's a 10-meter round trip. It takes about 3 milliseconds for sound to go 1 meter. And so to go out and back 10 meters is 30 milliseconds. So that means that you could take one of those measurements at a 30 hertz frame rate. And so if you imagine then raster scanning a beam over that thing, then you're talking about maybe once a second you're going to get an image. So it's just too slow. And so instead what we do is what's called receive beamforming. That's where we illuminate with kind of a flood of ultrasound. So we send a pulse that's essentially omnidirectional, and then we receive with multiple devices, and we do all of the receive signal processing in software. And so that's basically as fast as, it's essentially instantaneous in terms of the frame rate. So when you want to do very fast imaging, really receive beamforming is kind of the fastest way to do it, and the transmit beamforming is pretty slow. So, okay, so I managed to jump through the air ultrasonics. I'll talk about ultrasonic fingerprint sensors. So, Qualcomm is a company that has an ultrasonic fingerprint sensor product. We started, before the fingerprint sensor was in the iPhone at least, we started working on ultrasonic fingerprint sensors, and so we were working with InventSense and we had some press that was attracted by this. These are some images of the fingerprints that we could read. This was as of like 2016, and as I mentioned, InvenSense has kind of carried this into production, and they can show you higher resolution images that have much better contrast ratio because they pushed the technology a little bit further over the last 2 years. But first of all, let me talk about the strengths of ultrasonics versus optical fingerprint sensors. This is actually something that I sort of had a discussion with your former dean about 5 years ago when we first thought of this idea about why you would want to use ultrasonics versus optics. So this is a picture of an image with a mark across a fingerprint, and you can see the optical image basically doesn't have any of the features. You can't see any of the ridges and valleys on there because, again, when you have a black target, the optical system has a hard time seeing it. The optical ones are when you go through passport control, they're all optical. They're the best sensors available. Capacitive, everybody knows, is not a very good technology. It's only used in phones and laptops because it's the cheapest technology, but really optics is kind of the gold standard. And you can see here, this is an ultrasound image of the same fingerprint, and you can see, with the mark, ultrasound doesn't care about the color. And so this is a pretty remarkable image. John Schneider actually is a guy, this is 2008, he had a company called Ultrascan, and this is the product that Ultrascan made, and so it's gigantic, right? This is like the kind of thing that you would use at passport control. And so that's how it's able to get this very large ultrasonic image. You can look at how big your finger is, and you can look at your cell phone, you can realize the fingerprint sensor is much, much smaller than this. And so you might wonder how they're able to do this. Well, they had a system where they mechanically scan a single 40 megahertz transducer. It's focused at a single point, and they raster scan it over the finger to get that image. So you can build up a very large image. They can do detection. So your skin basically has the epidermis, which is the surface, and then there's a layer called the dermis, which is beneath that. And for very high security, they like to do dermal detection because it shows that it's a real fingerprint and not a spoofed, like an artificial printed fingerprint. The drawbacks of this is it's really big and it's mechanically scanned, so it's sort of slow. Ultrascan, actually it turns out, is the company that Qualcomm acquired to form the basis of their ultrasonic fingerprint sensor. So this was kind of John Schneider's idea about how to do this in 2008. There are other people who thought about how to do this. There's a company in the US called Sonovation that, if those of you who know what a conventional medical ultrasonic imager chip looks like, that's kind of what they're doing. They take a piezo ceramic piece and they sort of grind it to 100 micron thickness, then they dice it in 2 directions and they fill with a polymer layer. And so this is basically like when you go to the obstetrician and they're looking for, taking the images of the baby. It's kind of the same technology. And so Ultrascan thought that they would be able to make a fingerprint sensor using this, but just if you know what the cost pressures are on these things, you would stay from the beginning that this cannot possibly work. I mean, it works technically, but you'll never be able to sell it because the pricing pressure on these things is just, if you think about it, the competing technology is just CMOS, right? And in some cases, it's actually even simpler than that. They use basically a Kapton layer with capacitors on it. And so Kapton with like just a gold foil on it is super cheap, right? And so it's very hard to get this kind of technology where they talk about, the world's thinnest and epoxy encapsulated, ground and polished, designed, manufactured in the USA. None of those things are going to be low cost. And so this is a great technology from kind of a technology, it's like a hero project, but in terms of actually making it into the market, I'd be very, very skeptical that they'll do it. Qualcomm has a different approach, and they use TFT-based technology. It is piezoelectric, but they build a piezo layer on top of this is the same TFTs that are used in your display today. So these are glass plates. They can make them in very big sizes, and so that was kind of in the early days. They were thinking that you could do very big security applications, like something the size of your whole hand. And they can do 500 dpi, that's like a 25 micron or 50 micron pitch on the transducers. So it's a little bit of a different approach. The difficulty that they have is they don't have very good piezo materials, so they need very high voltages in this, and they have a tough time getting enough signal to noise ratio. And in particular, because the discussion about fingerprint sensors has shifted over the last 2 years since we sort of first published our stuff, really the way that the industry is going is to put the fingerprint sensor under the glass. And so there are many layers that are there, and so you get a lot of reflections, and so you need to begin with a very high SNR to be able to operate at that kind of distance and with those multiple layers. And so that is a challenge for Qualcomm. And so some of you may have seen, I mean, look, this paper was published in 2013, and so basically they had the technology available, but none of you have a phone that has this Qualcomm sensor in it. So clearly there are things that make this hard. So we had a different approach, and I'll go through it very quickly. What we did was we made Pimas, and they need to be covered with a polymer layer. In the lab we used PDMS, but there are other polymers that you could use. The idea is that these polymers have they have a matching acoustic impedance to the tissue of your skin. And so this is showing the fingerprint with ridges and valleys. What we do is we launch an ultrasound wave, and that was showing essentially like a plane wave where we're transmitting with all transducers at once. That was how we started working with the technology, transmitting a plane wave. We've since kind of moved to doing beamforming, where we can focus the ultrasound. But conceptually, this will give you an idea of how it works. We have a reflection off of the surface, and where there's air, we have a big impedance mismatch between the polymer layer, and so we get a reflection. So this area is going to look bright, and where your tissue is, we get transmission, and so it will look dark because we have a very small reflection there. Again, there is at the dermal layer, this is where your tissue is hydrated, so there's another, so versus your dry skin, there's another acoustic impedance difference, and so we can see that layer as well. And so we can get an image where if we're just recording the receive signals, if we look over time, the first echoes to arrive will be large, and they correspond to where the valleys are. And then later, at a distance equal to the thickness of your epidermis, we're going to get echoes here that correspond to the dermal layer. And those echoes are a little bit smaller, but we can still see them. And just to talk a little bit about fingerprints, there are what are called level 1 features, which are the pattern. And so these are whether you have like a left or a right loop, and whether it's a single loop or a double loop. These are really big, and so no fingerprint sensor on a phone actually uses level 1 features because none of the sensors are big enough. You can look at your own finger and see how big it is and compare it to the size of the fingerprint sensor die, which is about 3 millimeters on the side. Level 2 features are what are called minutia points. So that's where a ridge will terminate or where it branches, for example. And there are even level 3 features, which are, you see these little dots here, those are actually sweat pores. And those, again, are unique kind of indicators or markers of people. And so you can use these level 2 and level 3 features to do security. In addition, the other thing that you might be interested in is basically what's the distance between the epidermis and the dermis. That's about 200 microns. And so what happens is that these set the requirements to see these features. We need a 500 dpi image, and maybe even a little bit higher than 500 dpi to see the sweat pores. So that's the lateral resolution requirement. The axial resolution requirement, if we want to separate the image of the epidermis from the dermis, well, we have to be able to transmit a short pulse, so that essentially the received pulses from these 2 layers can't interfere, and so we better be able to separate layers that are 200 microns apart. That's a bandwidth requirement. And in turn, this tends to force us to use frequencies of, let's say, 20 megahertz or higher. So this is what the original array looks like that we made. This is from a paper that was published at the Solid State Circuits Conference in 2016. So the MEMS, each one of these little gold electrodes here is a PMUT, and they are sort of a thin multi-layer of aluminum nitride, and silicon was the passive layer that we used. So we have the top electrodes here, they're individual, and we share the bottom electrodes among the columns. So each of these kind of more faint things, a stripe of metal here, is the bottom electrode of this column of PMUTs. And we have 110 columns by 56 rows. And each of these little blue things here is a bond point. So we're basically bonding this MEMS array to CMOS. And you can see we have an individual connection to each top electrode and one connection to the bottom electrode. The pixels are about 50 microns, and like I said, that's what you need to have 500 dpi. And the other thing that matters is how big the fill factor is. So we've got a 50% fill factor. That means how much of the area is active versus being used for bond points and interconnect. That has an effect on how much sound pressure you can generate and sort of how efficient the array is overall. So there's over 6,000 pixels in this array, and we can read them out individually. And so what made this possible is we were actually using the production process that InventSense uses to make their inertial MEMS. This is an aluminum germanium eutectic bond between a MEMS wafer and a CMOS wafer. And so each of these little points here is where there's one of those aluminum germanium eutectic bond points. And what's shown here on the CMOS die is we have a separate receive amplifier beneath each of the PMATs. So that's basically a 50 micron square cell, which is plenty of room for a receive amplifier in 180 nanometer CMOS. And then we have a high voltage pulsar, one for each column. So that basically is showing kind of it's bonded to the bottom electrode here. And so that was the way that we separated basically the high voltage stage from the low voltage stage. These are all low voltage amplifiers, and these are all the high voltage. So they're actually separated by the Pima capacitors. When we transmit, we send a high voltage pulse through the bottom electrode, and we connect the top electrodes to ground. That basically protects the front end from that from being overloaded by that voltage there. And then when we receive, basically we are setting the high voltage to ground, and we're detecting the charge that's picked up on the top electrode. So we can transmit column by column and receive and read out each PMAT individually. We have an on-chip demodulator. As I mentioned, we're operating about 20 megahertz. We demodulate the signal, and then we just fed out that demodulated analog signal and digitized on a separate part on the board. And this is showing a cross-section of what this looks like. This was, you can see the CMOS layers. These happen to separate when we did the cross-sectioning. There are oxide anchors that connect the PMAT to the eutectic bonding region. This is the aluminum nitride layer, the molybdenum bottom electrode, and the silicon layer that's sort of the other layer of this unimorph structure. And you can see the CMOS metal layers is like metal 3, metal 4, metal 5 of the CMOS. So this is what the sensor looks like. It's about 4.5 by 3 millimeters in size. We bond the two chips together. You can see this is the CMOS in sort of full thickness. The MEMS is a little bit smaller, and the way that this works is that the bond pads are exposed at the edge of the CMOS die. So you can see in this photo a little bit more clearly. Here's the CMOS die, here's the bond pads, and this is the edge of the MEMS die. So the MEMS die is about 200 microns thick, and we use DRIE to etch away the middle of this thing. That exposes the thin PMAT layer. It sort of forms what I call a swimming pool. And then we fill that swimming pool with PDMS, and then that's the surface that you're touching with your finger. So the PMATs are very far away from where you're touching, but it is remarkably robust. I don't think that we ever saw any PMATs break due to people touching on them. We did see issues, where the PDMS would delaminate, but never problems with failure of a PMAT. And just to show, because this is a MEMS talk, so this is what the MEMS look like when they're vibrating up and down. This was measured with a scanning LDV. You got one cycle of vibration there. This was an earlier array that had 100 micron pitch, so it's a 250 dpi array. Let me see if I can show it again. There we go. Let's try to bring the page up and then. So we did these measurements initially because we weren't sure whether we would have totally uniform response. You can see some of the PMATs have a little bit larger amplitude than some of the others, and there is a little bit of a difference. If you look closely, you'll see that some of them, they reach their peak amplitude at different times. That's because there's a little bit of difference in the resonant frequency, so they're a little bit phase shifted relative to each other. This was measured in air. When we cover them with PDMS, you can imagine they're basically immersed in a fluid, and so they're much lower Q, and those effects are pretty much washed out. The way the measurements work is that we, as I mentioned, we transmit column by column, transmit a pulse, receive the echo, and that builds up the first stripe of the fingerprint image. And then we go to the next column and read out column by column and build up the whole fingerprint that way. And this is an actual picture of a fingerprint image taken with the sensor. So that process is really fast because we measure all 56 of these in a column simultaneously. We can also do beam forming where we use several columns to transmit together, and we can focus the image. That turns out to be important, particularly if you want to image at a longer distance, let's say through a glass surface. And just to show you that we can image now, I'll show you what a fingerprint image looks like. This is a photograph of the finger overlaid with the size of the imager. And we'll show we transmit, and receive, and this is the image that we get of the epidermis. So here you can see the fingerprint here. You can even see some dots here that are sweat pores, here, here, and here. And then we focus a little bit later. So we're just delaying the time that we're digitizing the image, and we have the image of the dermis. And so it looks also like the same fingerprint. If we overlay them on top of each other, you see that they're negatives. So where you have a bright region in the epidermal image, you have a dark region in the dermis. And just to show you that we can do this imaging at different depths, we made a phantom that was made of PDMS, and so on one layer it has a one-dimensional grading, and another layer we had the center logo, and this layer is 200 microns thick, and so we can basically laminate those on top of each other, and we take an image early to represent imaging on the finger surface, on the epidermis, and you can see the grading pattern, and then we image a little bit later, and you can see we're deeper into the phantom, and you can see our center logo. It's shaded by these bars, right? Because everywhere you have a reflection of the sound, it's kind of like the way that light would be blocked by an array of, let's say, stripes. And so there's always some shading there, but you can see that we can focus on the two different layers. And people always ask, well, if we're doing it column by column, it has to be slow. But we can image as fast as 380 frames per second because, again, we're running at 20 megahertz. It's relatively low energy to do an image. It's 280 microjoules, and so that's 2.8 milliwatts at 10 frames per second. And that's fast enough where you can slide your finger around. It's kind of like an ultrasonic camera. You can use it. So the other thing you want to be able to do is, again, if you want to operate underneath the screen, with my phone, the way I turn my fingerprint sensor on is I have to touch a button, right? But if you're operating through a screen, you don't have that ability to do the button touch. And so you have to have some other way of recognizing the user wants their fingerprint to be read. So you have to be we can basically operate in a mode where we're taking ultrasound images constantly, relatively slowly at 2 frames per second, and we're just looking at a small area. And from that small area, we can recognize that the user's finger is on top, and then it's time to fire up the whole array. And so you can do that at about 5 microwatts. And so that's a negligibly small amount of power for a phone, for example. So after more than 30 years, PMUTs are finally ready for consumer electronics. And I think that PMUTs and other piezoMEMS are going to have a big impact because of all the work that people at EPFL and other places have done on thin film piezo materials. In air, we have these tiny PMUTs that can work over now 5-meter range, and in tissue, we can make pulse echo fingerprint imaging again with a 1.8 volt supply. So I think this is really a technology that is ready for commercialization. And again, I'd like to thank all the students. There are lots of students that worked on this in my group at UC Davis, and then also in Bernhard Boser's group at UC Berkeley. And with that, I'll thank you and take any questions.
Thank you for this excellent overview on PMUTs and the advances in technology that have been made over the past 30 years. So we have time for questions.
Hello, thanks for the talk. I have a technical question. How difficult it is to save those membranes when it comes to aggressive, like processing, like dicing or packaging?
That's a good question. So what so the large membranes that we make for operation in air, we did at the university, we did wet sawing of wafers. And the biggest devices we were making at that time were about 0.5 millimeter in diameter. We've made bigger devices like that, bigger devices than 0.5 millimeter at chirp, so up to, let's say, 1 millimeter diameter. But we, in production, we use stealth dicing, laser dicing. So, and the reason we do that is because that is basically what everybody does for microphones today in production. And so every microphone packaging house has a stealth dicing system. So that basically just does, it sort of scores the wafer with a laser, and then you essentially are breaking it. They expand it on tape. So they score it and they expand the tape, and then that just works fine. And we don't have any issue with particulate or anything, and it's a totally dry process. So I can say that my experience at the university was with kind of smaller membranes. These are pretty thick. Like it sort of depends on what devices we've been making, but there's several microns thick, and there's no, we don't have like with a conventional capacitive microphone where you have, issues of stiction. So you can wet saw membranes okay, but for sure in production we use self-dicing, and it was just, partly because it was like we didn't have to think about it.
Hi, I have a few questions about the aluminum nitride and the fabrication of your Pimas.
Yes.
One question is, why are you using molybdenum instead of platinum?
We use molybdenum because it's easier to etch. We did use platinum early on, but we had a hard time patterning it very well. Yeah.
The other question is, why are you using such thick aluminum nitride? Have you guys considered scaling down in terms of the thickness, or?
Yeah, so I think actually that is a good idea for particularly for immersed transducers. Thinner is probably better, and I do have a student who's working on that. So I agree with that. It turns out that for air-coupled transducers, we tend to operate, so our devices are quite a bit thicker. And part of the reason that we do that is that we discovered early on, so like one of the things that we did was we were like very concerned about manufacturability. So can we make an 8-inch wafer where all the devices are the same? And so essentially, as you go thinner, you have a lot more sensitivity to stress. And so that tended to push us towards thicker devices. So the aluminum nitride layers, 1 micron or even more, are better for thick devices. Yeah.
Thank you.
A good question. In one slide, a cross-sectional view is shown where the utility bonding is used to connect the CMOS part and the sensor part.
Yeah.
Whereas the next slide, the wire bond is used to connect the stacked chips. So I wonder which is the real case in your chip.
Oh, the wire bonds here are to connect the. Oopsie. The wire bonds here are to connect to the package. So these are wire bonds on the CMOS. The bonding between the MEMS and the ASIC is actually inside here. You can't see it.
Okay.
Yeah.
Thank you.
Sure. Yeah, this was one of the questions. So if we had to do this, the problem if you have a separate MEMS die and an ASIC, you can make a what's called a swipe sensor. So that's basically a line of ultrasound transducers. You can make 256 or 512 pixels in a row. If you want to make a two-dimensional, in fact, those swipe sensors are one of the reasons why the fingerprint sensor didn't take off very well. It's hard to use them. And so you really need an area sensor, and that's just hard to do if you have the wire bond.
Hi, Professor. In your lecture, you have talked about two applications: the air bound and the tissue bound applications.
Mm-hmm.
Have you ever imagined other applications into different scenarios?
I think that, you could imagine doing other kinds of like solid wave ultrasound for maybe other applications. There's even a company that has commercialized a technology for touch sensing using ultrasound. And so what they do is they launch a solid wave in a glass panel, and essentially what you're doing is it's pulse echo detection, but the ultrasound is confined into the glass. And so then you can make a touch screen in pretty much anything. You could make touch surfaces in metal, for example, right? That where you can't use a conventional capacitive touch technology. So there's certainly interesting things that you could do with solid wave ultrasound. So what I would say is, in terms of kind of interesting things that people are doing with ultrasound, that's one of them. They also, that same company was making, you might know there's a phone that has a squeeze, like a force sensor. And so that same company has a technology to use that using ultrasound. So, and I'm not exactly sure what they detect there, but they're launching some kind of ultrasound wave in the side of the phone. And basically, as you grip it, you can squeeze it. And so they have things like you could, squeeze it to turn the camera on, or squeeze it to do some functionality. So you can do stuff like that with ultrasound. The other kind of thing that's interesting that people are doing, I'm not sure how practical this is, but it is pretty interesting, is there are people that are doing, they generate enough ultrasound that you can feel it. So there's a company called Ultrahaptics that is, they basically have very high pressure ultrasound that's directed at your hand, and they can make patterns that you can feel in the air. And there's kind of no other way to do that, so it's a pretty cool technology. They've had some demonstrations in cars where they're doing kind of a virtual touchscreen where you get touch feedback to know where you should press based on they're essentially projecting pressure field into the air, and you can basically make different things, different regions where you can distinguish where your hand is. So it's a pretty cool technology. I would say the limitation of that today is that they need a big ultrasound array. They need like 100 transducers, and so it's not cheap, and it uses a lot of power.
You spoke earlier about this technology from Qualcomm doing under-glass sensing on cell phones.
Yes.
So you said it was difficult because of the bad acoustic matching between glass and the skin. But I have another question about this is when you have a phone screen, you also have a lot of electronics below the screen.
Yes.
To show everything. So how do you, put the ultrasonic sensor inside and have a screen technology at the same time?
Yeah, that's definitely true. And so what I can say is that and it's different depending on whether you have kind of a conventional LCD display versus an OLED. And so there are people that have made ultrasound fingerprint sensors that will work through conventional but not yet OLED displays, because there are many different layers, as you mentioned, that will reflect, and you get reflections and you lose. You essentially are losing sound pressure level, and so it degrades your SNR. So it's hard. And it's one of the reasons I think that there's not anything that's shipping yet. There are rumors that I don't know whether they're true or not, but there are rumors that Apple had some kind of under the display fingerprint sensor that was prototyped and supposed to go in the iPhone 10, and it couldn't scale in production. So basically they can make it in the laboratory, but they can't make 100 million of them. And so that may be true. Certainly there's pretty good stories that say that the Force Touch is also very hard to manufacture. So sometimes there are things that we could do in the lab that's like very hard to scale into mass production.
So if there are no further questions, let's thank our speaker again.